this very moment, as you exist in the present, reality itself may be fracturing into an infinite cascade of parallel universes. Each quantum interaction, each subatomic decision, potentially births entire cosmos where alternate versions of you navigate divergent paths through existence. The multiverse, long relegated to the realm of science fiction and speculative fantasy, emerges from the mathematics of quantum mechanics not as whimsy, but as a profound possibility that challenges everything we understand about the nature of reality itself. The quantum realm operates by rules so strange, so fundamentally alien to our everyday experience, that even the greatest minds of the 20th century struggled to accept their implications. Yet these bizarre principles have given rise to a radical interpretation of quantum mechanics that suggests our universe is just one thread in an incomprehensibly vast tapestry of parallel realities, constantly splitting and diverging with every passing moment. This is the story of how serious science led to the most extraordinary claim ever made about the structure of existence, and why an increasing number of physicists believe the multiverse is not just possible, but inevitable. The birth of quantum strangeness. Our journey into the heart of parallel realities begins at the dawn of the 20th century, when the foundations of classical physics began to crack under the weight of experimental evidence that defied explanation. In laboratories across Europe, physicists encountered phenomena that made no sense within the elegant framework Isaac Newton had constructed centuries earlier. Light behaved in ways that seemed impossible. Atoms released energy in discrete packets rather than continuous streams, and matter itself exhibited properties that blurred the line between particle and wave. In those early decades, a constellation of brilliant minds converged on the problem. Albert Einstein, Max Planck, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and others began constructing a new framework for understanding the subatomic world. This framework, quantum mechanics, proved remarkably successful at predicting experimental outcomes. By accepting the strange duality of light, treating it simultaneously as both particle and wave, physicists unlocked solutions to problems that had seemed intractable. The theory worked with stunning precision, making predictions that experiments confirmed again and again. Yet beneath this success lurked something deeply unsettling, a feature of quantum mechanics so profoundly strange that it threatened the very notion of an objective, deterministic reality. Classical physics had always been exact and definitive. We could measure the precise position of Earth in its orbit, calculate the exact velocity of a spacecraft, determine with certainty the mass of an object. Every physical quantity possessed a definite, measurable value that existed independent of our observation. The universe operated like clockwork, its future state entirely determined by its present configuration and the laws of physics. Quantum mechanics shattered this reassuring picture. In the quantum realm, nothing possessed definite values until measured. Instead of certainty, physicists found only probabilities, clouds of potential outcomes described by a mathematical construct called the wave function. This wave function encoded all possible states a quantum system could occupy, assigning each a probability of being observed. An electron's position wasn't a single point, but a probability distribution spread across space. Perhaps there existed a 25% chance of finding it here, another 25% chance of finding it there, and a 50% chance of discovering it somewhere else entirely. The wave function itself obeyed precise mathematical laws. Schrödinger's equation, one of the masterpieces of 20th century physics, described exactly how this wave function evolved through time. The mathematics was elegant, deterministic, and perfectly predictive, yet what it predicted was not definite outcomes, but probability distributions. The wave function evolved smoothly and continuously, encompassing all possibilities simultaneously, until something happened that seemed to defy physical explanation. The Copenhagen collapse. In the 1920s, Niels Bohr and Werner Heisenberg developed an interpretation of quantum mechanics that would dominate physics for decades. According to the Copenhagen interpretation, named for Bohr's home city, The wave function represented a real physical entity describing a quantum system in a state of superposition, simultaneously existing in all possible states. This superposition persisted until an observation occurred, at which point the wave function suddenly collapsed to a single definite outcome. One possibility became reality while all others vanished as if they had never existed. This collapse mechanism felt deeply strange. Why should the act of observation, of measurement, possess such extraordinary power over physical reality? What made observers special? Did the universe behave differently when someone was watching versus when no conscious being paid attention? The Copenhagen interpretation offered no mechanism for wave function collapse, no explanation for what constituted an observation, or why measurements possess this almost magical ability to crystallize reality from a haze of possibilities. Albert Einstein found the Copenhagen interpretation philosophically repugnant. His entire scientific career had been built on the conviction that nature operated according to rational, deterministic laws, that the universe possessed an objective reality independent of observers. The idea that God played dice with the cosmos, that fundamental randomness lay at the heart of physical law, struck Einstein as absurd. He spent decades searching for hidden variables, deeper layers of reality that would restore determinism to physics and eliminate the apparent randomness of quantum measurements. Erwin Schrödinger shared Einstein's discomfort with the Copenhagen interpretation, and in 1935 he devised a thought experiment to illustrate its apparent absurdity. Imagine, Schrödinger proposed, a cat sealed inside a box, with a quantum device containing a radioactive atom, a Geiger counter, a hammer, and a vial of poison. The radioactive atom existed in quantum superposition, simultaneously decayed and not decayed. If the atom decayed, the Geiger counter would detect it, trigger the hammer, break the vial, and kill the cat. If the atom remained intact, the cat would live. According to the Copenhagen interpretation, until someone opened the box and observed the system, the cat existed in superposition, simultaneously alive and dead. Only when an observer looked inside did the wave function collapse, forcing reality to choose between a living cat and a dead one. The thought experiment was meant to demonstrate the absurdity of applying quantum rules to macroscopic objects, yet it also highlighted a genuine mystery at the heart of quantum mechanics. If quantum superposition applied at the atomic scale, and atoms composed cats, where exactly did superposition end and definite classical reality begin? Despite these philosophical difficulties, quantum mechanics worked extraordinarily well. Its predictions matched experimental results with unprecedented precision. The theory enabled the development of nuclear energy, transistors, lasers, and countless other technologies that transformed human civilization. Computer processors, wireless communication, LED lighting, GPS navigation, smartphones, all these marvels of modern technology rested on quantum mechanical principles. Physicists could use quantum mechanics as a practical tool while remaining agnostic about its deeper meaning, but the interpretive question refused to go away. What was quantum mechanics really telling us about the nature of reality? The many worlds revolution. In 1957, a 27-year-old American physicist named Hugh Everett III completed his doctoral dissertation at Princeton University. Working under the supervision of John Archibald Wheeler, one of the most creative theoretical physicists of the era, Everett proposed a radical reinterpretation of quantum mechanics that would eventually revolutionize how many physicists understood reality. His central insight was simultaneously simple and profound. What if the wave function never collapsed at all? What if every possible outcome, encoded in the wave function, actually occurred, each in its own separate universe? Consider a simple quantum system, a single electron about to make a measurement that could produce two possible outcomes. Perhaps the electron's spin could be measured as up or down, or its position detected on the left or right side of an apparatus. According to the Copenhagen interpretation, these two possibilities existed in superposition within the wave function, each assigned a particular probability. The wave function encoded both outcomes simultaneously. But when measurement occurred, collapse happened. One outcome manifested in reality while the other disappeared, banished to the realm of might-have-beens. Everett proposed abandoning wave function collapse entirely. Instead, he suggested that both outcomes occurred, but in separate, non-interacting branches of reality. When the electron's spin was measured, the universe split into two equally real universes. In one universe, the electron's spin was up. In the other, the spin was down. Crucially, these universes couldn't communicate or interact after the split. They became causally isolated from each other, separate threads of reality that diverged at the moment of quantum measurement. This process, which physicists would later call branching or splitting, didn't happen just once. Every quantum interaction that produced multiple possible outcomes triggered a branching event. And because the universe contained an incomprehensible number of particles, each constantly engaged in quantum interactions, the branching occurred continuously at an effectively infinite rate. Every moment of existence produced an exponentially growing tree of parallel universes, each representing a different sequence of quantum outcomes. In this interpretation, your consciousness wasn't choosing which outcome to experience. Rather, your consciousness split along with the universe. At each branching point, multiple versions of you came into existence, each experiencing one of the possible outcomes. From your subjective perspective, you experienced only one outcome, but that didn't mean the others failed to occur. Alternate versions of you, possessing their own continuity of consciousness and memory, existed in their own universes, each convinced their particular outcome was the one true reality. The elegance of Everett's interpretation was that it took quantum mechanics completely seriously, without adding any extra postulates or mysterious collapse mechanisms. The wave function evolved according to Schrödinger's equation, which was deterministic and perfectly well understood. There was no need to specify when or how collapse occurred, no need to define what constituted an observer or a measurement. The mathematical formalism of quantum mechanics, taken at face value, naturally implied a constantly branching multiverse. Everett wasn't adding extra worlds to the theory. He was simply reading off what the mathematics already said. Wheeler, Everett's advisor, found the idea fascinating but troubling. He helped Everett present the work to Niels Bohr in Copenhagen, hoping the father of quantum interpretation might embrace this new perspective. Bohr's response was devastating. He found the many worlds interpretation extravagant beyond justification, an unnecessarily profligate multiplication of realities to avoid a perfectly serviceable interpretive framework. The wider physics community largely agreed. The Copenhagen interpretation, despite its philosophical difficulties, worked perfectly well for practical purposes. Why complicate matters by proposing an infinity of undetectable parallel universes? Faced with this rejection, Everett left academic physics, taking a position at the Pentagon where he worked on nuclear war game theory and optimization problems. He never published another physics paper, though he remained convinced his interpretation was correct. For years, the many worlds interpretation languished in obscurity, discussed occasionally but generally dismissed as an interesting but unnecessary elaboration of quantum mechanics. Decoherence and the revival. The resurrection of many worlds began in the 1970s with the development of a crucial concept called quantum decoherence. This breakthrough, developed by physicists, including Wojciech Zurek and others, provided the missing piece that transformed many worlds from a speculative curiosity into a serious competitor to the Copenhagen interpretation. Decoherence explained why we never actually observe quantum superpositions in everyday life, why Schrödinger's cat appears to be either alive or dead rather than existing in a blur of both states simultaneously. The key insight concerned the relationship between quantum systems and their environments. In idealized theoretical models, physicists often consider isolated quantum systems sealed off from any external influence. In such perfect isolation, a quantum system maintains coherence. The wave function evolves smoothly and predictably according to Schrödinger's equation, and the various possibilities encoded in superposition remain perfectly distinguishable, able to interfere with each other and produce the characteristic wave patterns that reveal quantum behavior. Real quantum systems, however, never exist in perfect isolation. Any system in the actual universe constantly interacts with its environment, bombarded by photons, air molecules, thermal vibrations, and countless other influences. These environmental interactions cause the quantum system to become entangled with its surroundings, correlating the system's quantum state with the states of innumerable environmental particles. This entanglement doesn't collapse the wave function in the Copenhagen sense, but it does something equally important. It suppresses the interference between different outcomes, making them effectively classical and definite from the perspective of any observer embedded in that environment. This process, quantum decoherence, happens extraordinarily quickly for macroscopic objects. A cat, composed of countless atoms, all interacting with their environment, decoheres, essentially, instantaneously. The different branches corresponding to a live cat and dead cat states become entangled with different environmental states so rapidly that they can no longer interfere with each other. From the perspective of an observer within one branch, the cat appears to have a definite state. The observer doesn't see superposition because decoherence has already separated the branches. Crucially, decoherence provides exactly what the many worlds interpretation needed. It explains why, despite the absence of wave function collapse, we nonetheless observe definite outcomes rather than fuzzy superpositions. The various branches of the universal wave function are all equally real. All continue to evolve according to Schrödinger's equation, but they rapidly become isolated from each other through environmental entanglement. An observer in one branch cannot detect the other branches because decoherence has destroyed the coherence necessary for interference. From the perspective of the Copenhagen interpretation, decoherence makes wave function collapse appear to occur, providing a mechanism for the transition from quantum to classical behavior. But many worlds advocates pointed out that decoherence achieved this without actually requiring collapse. The wave function never truly collapsed. All outcomes remained encoded in the universal wave function. Decoherence simply made the different branches causally and observationally isolated from each other, creating the appearance of a single classical reality. Armed with a decoherence framework, the many worlds interpretation gained new respectability. It could now answer the most damaging objection, the question of why we don't observe superpositions in everyday life. The interpretation also possessed certain theoretical virtues that Copenhagen lacked. It was fully deterministic at the level of the universal wave function. There was no need to specify when measurement occurred, or what constituted an observer. The theory didn't require adding any new postulates beyond standard quantum mechanics. It simply took the existing formalism seriously. Throughout the late 20th and early 21st centuries, many worlds steadily gained adherence. Surveys of physicists showed increasing support for the interpretation, though it remained a minority position compared to Copenhagen. By some recent estimates, approximately 20% of physicists favor many worlds, a remarkable rise for an interpretation that was nearly forgotten decades earlier. The interpretation attracted particularly strong support from theoretical physicists working on quantum cosmology and quantum gravity, fields where the role of observers becomes problematic and where a fully quantum mechanical description of the entire universe seems necessary. Quantum computers and parallel computation. The rise of quantum computing in recent decades has provided what some physicists consider indirect evidence for the many worlds interpretation. Quantum computers operate by harnessing the strange properties of quantum superposition and entanglement to perform computations impossible for classical computers. Where classical computers process information using bits that exist in definite states of 0 or 1, quantum computers use quantum bits, or qubits, that exist in superpositions of both states simultaneously. A classical computer with 300 bits can represent any one of 2 raised to the 300th power different numbers at a given time. A quantum computer with 300 qubits, however, can exist in a superposition representing all 2 raised to the 300th power numbers simultaneously. When a quantum algorithm is executed, the computer effectively performs computations on all these superposed values in parallel, using interference between the different possibilities to extract the answer. The computational power scales exponentially with the number of qubits, giving quantum computers an enormous advantage for certain types of problems. David Deutsch, a pioneering quantum computing theorist and vocal advocate for many worlds, argues that quantum computers provide evidence for the multiverse. When a quantum computer with 300 qubits performs a computation, where is the processing actually happening? The physical device exists in ordinary space, yet it's somehow processing 2 raised to the 300th power different values simultaneously. That number exceeds the estimated number of atoms in the observable universe by an incomprehensible margin. Where, Deutsch asks, are all those computations being performed? His answer: in parallel universes. According to the many worlds interpretation, when a quantum computer places its qubits in superposition and executes an algorithm, the universal wave function branches into all possible computational paths simultaneously. Each branch performs one piece of the computation. The quantum algorithm is designed so that interference between branches amplifies the correct answer while canceling incorrect ones. When the final measurement is performed, decoherence causes the branches to separate, and an observer in each branch sees what appears to be a single definite answer. The computation's power comes from harnessing resources distributed across the multiverse. Not all physicists accept this interpretation of quantum computing. Critics argue that the computational process can be fully explained using the mathematics of quantum mechanics without needing to invoke parallel universes. The superposition of qubits is a quantum state, and quantum states evolve according to well-understood equations. There's no need to imagine actual parallel computations in separate universes. The mathematics describes what happens completely, and ontological interpretations about what exists beyond our observations remain matters of philosophical preference rather than scientific necessity. Yet Deutsch and others maintain that the many worlds interpretation provides the most natural and economical explanation for quantum computing power. Rather than treating superposition as a mathematical abstraction, many worlds regards it as physically real, with each term in the superposition corresponding to an actual universe. The parallelism of quantum computation becomes literal parallelism across branches of the multiverse. This perspective, they argue, gives quantum computing a clearer conceptual foundation and helps guide the development of new quantum algorithms. The debate illustrates a fundamental tension in modern physics. Quantum mechanics provides a mathematical framework that makes extraordinarily accurate predictions. But physicists remain divided about what that mathematics tells us about reality. Does the wave function represent something physically real, or is it merely a tool for calculating probabilities? Do parallel universes actually exist, or is the multiverse just a colorful way of talking about quantum states? These questions remain unresolved, not because of any failure of quantum theory, but because quantum mechanics itself is compatible with multiple interpretations that make identical predictions for all observable phenomena. The nature of branching. Understanding how branching works in the many worlds interpretation requires grappling with some subtle conceptual points. First, the branching isn't something that happens to the universe from an outside perspective. There is no external vantage point from which we could watch universes splitting like cells dividing. Instead, branching is a structure that emerges from the mathematics of quantum mechanics when applied to the entire universe. The universal wave function, which describes the quantum state of everything that exists, evolves according to Schrödinger's equation. This evolution is completely smooth and continuous, with no sudden jumps or discontinuities. When we say branching occurs, we mean that the universal wave function develops a structure where different terms become decohered and isolated from each other. These terms correspond to what we call different branches or different worlds, but they all exist within the single, continuously evolving universal wave function. From the perspective of an observer embedded within the system, branching appears to happen whenever a quantum measurement produces a definite outcome. Before the measurement, the observer exists in a superposition of states corresponding to different possible measurement results. After decoherence, multiple versions of the observer exist in different branches, each experiencing one of the possible outcomes. Subjectively, each version experiences a single definite result and remains unaware of the other branches. This leads to a peculiar feature of many worlds. From a God's eye view, if such a perspective made sense, nothing unpredictable ever happens. The universal wave function evolves deterministically according to Schrödinger's equation. All possibilities encoded in the wave function occur in different branches. But from the perspective of any individual observer within a branch, quantum mechanics appears fundamentally random. Each version of you experiences a particular sequence of quantum outcomes, and before a measurement, you cannot predict which branch your consciousness will find itself in. Some philosophers and physicists find this troubling. If all outcomes occur in different branches, what determines which branch contains you? The many worlds interpretation offers an answer based on the squared amplitude of the wave function, which determines the probability weight or measure assigned to each branch. Branches with higher measure are in some sense more real or more typical, though all branches exist. When you perform a quantum measurement, you should expect to find yourself in a higher measure branch, which explains why quantum probabilities work the way they do. The nature of personal identity becomes strange in this framework. Before a quantum measurement with two possible outcomes, there is one version of you. After the measurement and subsequent decoherence, there are two versions, each with equal claim to being the continuation of the original person. Both have your memories, your personality, your sense of continuous identity. Neither is more authentically you than the other. This raises philosophical questions about the nature of consciousness and personal identity that go beyond physics itself. Another question concerns when branching happens. At what point does the universe split into separate worlds? The answer depends somewhat on what we mean by separate. If we mean causally isolated, in the sense that interference between branches is suppressed, then branching happens whenever decoherence occurs, which is essentially immediately for macroscopic systems, but can take longer for carefully isolated quantum systems. If we mean that the branches have diverged enough to represent meaningfully different histories, then branching is more gradual. Small quantum differences initially make negligible differences to macroscopic outcomes, but over time, these small differences can amplify through chaotic dynamics. The many worlds interpretation also faces the challenge of explaining the apparent special status of certain variables. When we say the universe branches, we typically mean it branches into different outcomes for measurements of position, or spin, or other observables that physicists can actually measure. But the mathematical formalism of quantum mechanics doesn't single out any particular set of variables as special. Different choices of observable lead to different decompositions of the wave function into branches. This is known as the preferred basis problem, and while decoherence provides much of the answer by selecting certain observables as naturally stable against environmental interaction, some ambiguity remains. Despite these subtleties and ongoing debates about details, the core claim of many worlds remains straightforward. If we take quantum mechanics seriously, if we accept that the wave function provides a complete description of physical reality and evolves according to Schrödinger's equation without collapse, then the existence of multiple branches representing different quantum outcomes follows naturally. The interpretation doesn't add anything to quantum mechanics. It simply accepts what the mathematics already says. Quantum immortality. The many worlds interpretation leads to a thought experiment so strange that even many advocates of the interpretation hesitate to embrace its implications. The idea, known as quantum immortality, suggests that from your subjective first-person perspective, you might never experience your own death. This possibility emerges from taking seriously the claim that your consciousness exists in every branch where you remain alive. Imagine a scenario where you face a life-threatening quantum event. Perhaps you're subjected to a quantum Russian roulette game where a quantum measurement determines whether a lethal device activates. According to many worlds, the universe branches into outcomes where you survive and outcomes where you die. In branches where you die, your consciousness ceases, and there is no subjective experience of those branches. But in branches where you survive, your consciousness continues, and you remain aware of your existence. From your first-person perspective, you can only ever find yourself in branches where you remain alive. You cannot experience the branches where you die, because in those branches, you cease to have experiences. Therefore, no matter how many quantum life or death situations you encounter, you will always subjectively experience survival, because you can only experience branches where survival occurred. Your consciousness appears to be guided along an immortal path through the branching structure of reality. The implications become even stranger when considering the aging process and natural death. While most aspects of biology are effectively classical and deterministic, quantum events occasionally play crucial roles in biological processes. Mutations are sometimes caused by quantum tunneling of atoms in DNA. Certain neural processes might have quantum aspects. If any quantum event could make the difference between life and death, between healthy aging and fatal illness, then the argument suggests your consciousness would always find itself in the branches where you remain alive. Hugh Everett himself apparently believed something like this. According to secondhand accounts from colleagues and family members, Everett was convinced that his many worlds theory guaranteed him a form of immortality. He never explicitly wrote about quantum immortality in his published work, maintaining scientific respectability by confining his papers to technical details and avoiding speculative philosophy. But in private conversations, he reportedly expressed confidence that his consciousness would persist indefinitely, always finding itself in some branch where he remained alive. The irony is profound. Everett lived an unhealthy lifestyle, chain-smoking cigarettes, drinking heavily, and largely ignoring medical advice. He died of a heart attack at age 51 in 1982, a quarter century after proposing the many worlds interpretation. If he truly believed in quantum immortality, his lifestyle choices suggest he might have been betting his life on his theory being correct. Of course, from his subjective perspective in those branches where he survived, perhaps he continues to believe his theory's correctness has been vindicated. Most physicists who accept many worlds reject quantum immortality as a coherent consequence of the interpretation. They point out that the argument conflates the existence of branches where you survive with the probability measure assigned to those branches. While it's true that branches where you survive continue to exist, the measure associated with those branches decreases over time as you age and face more ways to die. Eventually, the vast majority of the measure is concentrated in branches where you're dead, even though some infinitesimal measure remains in branches where you survive against absurd odds. Another objection concerns the nature of survival. Quantum immortality arguments typically focus on discrete life or death events, but aging is a gradual process of accumulating damage. In branches where you survive to extreme ages, you might be so severely debilitated by illness and injury that calling it survival seems generous. Your consciousness might persist, but in a state of extreme suffering and cognitive decline. The thought experiment ignores the distinction between mere biological persistence and anything resembling a worthwhile continued existence. Furthermore, quantum immortality seems to predict that you should expect to find yourself in increasingly improbable situations as you age. If your survival depends on unlikely quantum events, you should experience bizarre circumstances where you narrowly escape death through unlikely accidents and coincidences. The measure of branches where you experience normal aging patterns should decrease relative to branches where you survive through quantum miracles. Yet we don't observe this effect. People age normally and die at statistically expected rates, suggesting that quantum immortality doesn't match our actual experience. The thought experiment does, however, illuminate something important about the subjective experience of branching. In the many worlds interpretation, your future is not a single timeline, but a branching tree of possibilities, weighted by quantum probability amplitudes. Every version of you that exists has an equal claim to being the real you, the continuation of your current consciousness. This raises profound questions about anticipation and rational decision-making in a branching universe, questions that philosophers and physicists continue to debate. The measure problem. One of the deepest challenges facing the many worlds interpretation involves explaining where quantum probabilities come from. In the Copenhagen interpretation, probabilities are fundamental. The wave function collapse is inherently random, with probabilities given by the Born rule, which states that the probability of an outcome is proportional to the squared amplitude of the corresponding term in the wave function. This rule matches experimental observations perfectly, but Copenhagen offers no explanation for why this particular rule holds, rather than some other probability assignment. Many worlds faces a different version of the problem. If all outcomes occur in different branches, what does probability even mean? You might think that since everything happens, each outcome has probability 1 of occurring in some branch. But this contradicts our experience. When we perform a quantum measurement with two possible outcomes, one having 90% probability and the other 10%, we typically observe the high probability outcome. Many worlds needs to explain why, if both outcomes occur with certainty in different branches, we experience the frequency distribution predicted by the Born rule. The answer involves the notion of measure or weight assigned to different branches. Not all branches are equal. The universal wave function assigns different amplitudes to different terms, and these amplitudes determine the measure of the corresponding branches. When you perform a measurement, you should expect to find yourself in a branch with higher measure, just as you would expect to find yourself in a random sample drawn from a population that contains more of one type than another. The Born rule emerges from this measure-theoretic structure. However, deriving the Born rule from the basic postulates of many worlds has proven challenging. Why should measure be determined by the squared amplitude of the wave function rather than the amplitude itself or some other function? Various attempts have been made to derive the Born rule from symmetry principles, decision-theoretic arguments, or other fundamental considerations. Some approaches show promise, but no derivation has achieved universal acceptance. The measure problem remains an active area of research and debate. Related to the measure problem is the question of what happens to measure over time as branching occurs. Each branching event creates new branches, but the total measure across all branches remains conserved. This means that the measure associated with your current branch continuously decreases as branching occurs, being subdivided among the daughter branches. Should you care about this decreasing measure? Does it matter for your anticipations and decisions? These questions about the significance of measure touch on deep issues about personal identity, consciousness, and rationality in a branching universe. Some critics argue that the measure problem reveals a fatal flaw in many worlds. If the interpretation cannot derive the Born rule from first principles, if it must simply postulate the measure structure as an additional axiom, then it loses one of its main advantages over Copenhagen. Both interpretations end up needing to postulate something about probabilities or measures without deeper justification. Advocates respond that deriving the Born rule remains an active research program with promising leads, and that even if some postulates about measure are needed, many worlds still has fewer and simpler axioms than Copenhagen, with its collapse postulate. Evidence and testability. A common criticism of the many worlds interpretation is that it makes no testable predictions different from other interpretations of quantum mechanics. All interpretations reproduce the same experimental outcomes because they're all interpretations of the same underlying mathematical formalism. If many worlds cannot be distinguished experimentally from Copenhagen or other interpretations, critics ask, what makes it a scientific theory rather than mere metaphysical speculation? Advocates of many worlds respond that testability isn't the only virtue of a scientific theory. Simplicity, elegance, consistency with other theories, and explanatory power all matter. Many worlds scores well on these criteria. It requires no additional postulates beyond standard quantum mechanics. It's fully deterministic and local. It doesn't require mysterious wave function collapse or a special role for observers. It extends quantum mechanics to the entire universe without modification. These theoretical virtues make many worlds attractive even if it's not directly testable. Moreover, some physicists argue that indirect tests are possible. The development of quantum computers might eventually distinguish between interpretations if different interpretations lead to different approaches to quantum algorithm design or different expectations about the limits of quantum computation. Tests of quantum mechanics in increasingly macroscopic systems could potentially reveal deviations from standard predictions that favor one interpretation over others, though no such deviations have been found despite decades of increasingly sophisticated experiments. The interpretation question also becomes crucial in attempts to formulate quantum theories of gravity and quantum cosmology. In these contexts, the entire universe is the quantum system, and there are no external observers. Copenhagen's reliance on measurement and observers becomes problematic when applied to the universe as a whole. Many worlds, treating the wave function as objectively real and evolving deterministically, extends more naturally to quantum cosmology. If future theories of quantum gravity make different predictions depending on which interpretation of quantum mechanics is adopted, those predictions could provide tests. Some proposals suggest that evidence for many worlds might come from observations in quantum cosmology. If the universe itself is described by a quantum wave function, then the cosmological parameters we observe, like the strength of dark energy or the amplitude of primordial density fluctuations, might be explained by anthropic selection across branches of the cosmological wave function. Different branches would have different parameter values, and we necessarily observe values compatible with our existence. If this anthropic reasoning produces successful predictions that wouldn't follow from other approaches, it could constitute evidence for the reality of the multiverse implied by many worlds. Another possibility involves future understanding of consciousness and its relationship to quantum mechanics. Some approaches to the quantum measurement problem, including objective collapse theories, suggest that consciousness plays a fundamental role in wave function collapse. If neuroscience eventually reveals that consciousness is entirely classical, with no special quantum aspects, this might disfavor interpretations that give consciousness a fundamental role while supporting interpretations like many worlds that treat consciousness as an emergent classical phenomenon, supervening on quantum substrates. Philosophical implications. The many worlds interpretation raises profound philosophical questions that extend far beyond physics. If the interpretation is correct, the implications reshape our understanding of existence, identity, choice, and meaning in ways both exhilarating and disturbing. Every decision point, every quantum measurement, every moment of existence spawns countless alternate versions of ourselves navigating different paths through reality. The life you experience is just one thread in an incomprehensibly vast tapestry of parallel lives. Consider the nature of choice and moral responsibility in a branching universe. When you face a decision, different versions of you make different choices in different branches. If you face a moral dilemma and choose the ethical path in one branch, while your alternate self chooses wrongly in another branch, what does this mean for moral responsibility? Are you praiseworthy for the good choice when an alternate you made the bad choice? Does the existence of branches where you choose differently diminish the significance of the choices you actually make? Many worlds advocates argue that the branching structure doesn't undermine moral responsibility or the significance of choice. From your subjective perspective, you make genuine decisions that shape your future experiences. The fact that other versions of you make different choices in other branches doesn't make your choices any less real or consequential for your own continued existence. You remain responsible for the decisions made by the version of you that inhabits your particular branch. The interpretation also raises questions about personal identity and the nature of the self. Before a major branching event, there is one version of you. Afterward, there are multiple versions, each with equal claim to being your continuation. In what sense are these various versions all you? Is personal identity something that can split and diverge? Or does the splitting create new people who merely share your past? If you knew for certain that many worlds was correct, and that a quantum event was about to create two future versions of you having very different experiences, how should you feel about this prospect? Some philosophers suggest that the branching structure of many worlds provides a new framework for thinking about personal identity and survival. Rather than identity being an all-or-nothing relation, it might be a matter of degree, with different future branches having different strengths of identity connection to your present self, weighted by quantum measure. This connects to older philosophical debates about personal identity in cases of teleportation, brain splitting, and other thought experiments that create multiple candidate continuations of a single person. The question of meaning in a many worlds universe is perhaps the most psychologically challenging. If every possibility occurs somewhere in the multiverse, if every choice is made and every path explored by some version of you, does anything you do truly matter? When success and failure, triumph and tragedy, all happen with certainty in different branches, what weight should we give to the particular outcomes we happen to experience in our branch? Here again, many worlds advocates emphasize the first-person perspective. From your subjective viewpoint, you experience only one branch. The outcomes in your branch are the ones that matter to you because they're the ones you'll experience. The fact that other outcomes occur elsewhere doesn't diminish the reality or significance of your actual experiences and outcomes. Your life remains meaningful in the same way it would be in a single-world universe, because subjectively you inhabit only one thread of the multiverse. Yet the knowledge that alternate versions of yourself are living different lives, making different choices, experiencing different outcomes, creates a strange kind of cosmic loneliness. You can never meet these alternate selves, never compare your choices and experiences with theirs, never learn whether you made better or worse decisions than the versions of you in other branches. Each version of you is trapped in their own branch, aware that countless variants exist, but forever unable to interact with them. Current status and future directions. Today, the many worlds interpretation occupies an unusual position in physics. It has substantial and growing support among theoretical physicists, yet it remains controversial and far from universally accepted. Surveys show roughly 20% of physicists favor the interpretation, a significant minority, but still well behind the Copenhagen interpretation. Among physicists working on quantum foundations, quantum information theory, and quantum cosmology, support is higher, sometimes approaching majority status. The interpretation benefits from several recent developments in physics. Quantum computing has made the abstract mathematics of superposition and entanglement more concrete, providing what some see as evidence for parallel quantum computation across many worlds. Advances in understanding decoherence have made the interpretation more sophisticated and better able to explain the emergence of classical reality from quantum substrates. Work in quantum cosmology and quantum gravity has highlighted the difficulties of applying Copenhagen-style interpretations to the universe as a whole, making many worlds more attractive for fundamental physics. At the same time, the interpretation faces ongoing challenges. The measure problem remains unsolved to everyone's satisfaction, with no universally accepted derivation of the Born rule from first principles. The preferred basis problem, while much illuminated by decoherence theory, retains some controversial aspects. Questions about the nature of probability, personal identity, and rational decision-making in a branching universe continue to generate philosophical debate. Alternative interpretations of quantum mechanics continue to be developed and defended. Objective collapse theories, which modify quantum mechanics to include spontaneous wave function collapse as a physical process, offer a different resolution of the measurement problem. De Broglie-Bohm pilot wave theory provides a deterministic hidden variable interpretation. Various information, theoretic, and relational interpretations reframe the entire question. The interpretive landscape remains rich and contested, with no consensus in sight. Looking forward, several developments might influence the status of many worlds. Continued progress in quantum computing could potentially reveal distinctive predictions of different interpretations, particularly regarding the ultimate limits of quantum computation. Advances in testing quantum mechanics in larger and more complex systems might uncover unexpected phenomena that favor one interpretation over others. Success or failure in formulating consistent theories of quantum gravity within different interpretive frameworks could shift opinion. The intersection of quantum mechanics with the study of consciousness might also prove decisive. If consciousness turns out to have irreducible quantum aspects that play a role in wave function collapse, this would challenge many worlds and support interpretations that give consciousness a fundamental role. Conversely, if consciousness is entirely explained by classical neuroscience as an emergent phenomenon supervening on quantum substrates, this would support many worlds' treatment of observers as purely physical systems subject to the universal wave function. Perhaps the deepest question is whether the interpretive debate can ever be resolved by empirical evidence, or whether it will remain a matter of philosophical preference among empirically equivalent frameworks. Some physicists argue that focusing on interpretations is a distraction from the productive work of calculating predictions and designing experiments. Others maintain that interpretation matters deeply for understanding what quantum mechanics reveals about reality, for guiding the development of new theories, and for ensuring that physics provides genuine insight rather than mere computational recipes. The story of parallel worlds emerging from quantum mechanics represents one of the most extraordinary developments in the history of science. What began as an attempt to understand atomic spectra and radioactive decay evolved into a theory that challenges our most basic assumptions about the nature of reality. Whether the many worlds interpretation proves correct, whether countless parallel versions of ourselves truly exist in causally isolated branches of a universal wave function, remains uncertain. But the mere fact that serious physics led to such a remarkable possibility demonstrates the profound strangeness of the quantum world and the continuing power of science to overturn our understanding of existence itself. Alternative interpretations and their challenges. The many worlds interpretation stands as just one possible resolution to the quantum measurement problem, though perhaps the most radical. Throughout the century-long history of quantum mechanics, physicists and philosophers have proposed numerous alternative frameworks, each attempting to reconcile the mathematical formalism with our observations while avoiding what its proponents view as the weaknesses of competing approaches. Understanding these alternatives illuminates both the strengths and limitations of many worlds while revealing the depth of the interpretive crisis at the heart of quantum theory. The Copenhagen interpretation, despite being the oldest and most widely taught approach, exists in multiple variants rather than as a single coherent framework. Niels Bohr's original formulation emphasized complementarity, the idea that wave and particle descriptions are mutually exclusive but equally necessary for a complete understanding of quantum phenomena. Werner Heisenberg stressed the role of the uncertainty principle and the disturbance caused by measurement. Later versions incorporated elements from multiple founders, creating a somewhat ambiguous tradition rather than a precise interpretive stance. All Copenhagen variants share certain features. They treat the wave function as a tool for calculating probabilities rather than a representation of physical reality. They maintain a fundamental divide between the quantum realm and the classical world of measurement apparatus and observers. They incorporate wave function collapse as a basic postulate without attempting to explain its mechanism. And they generally adopt an instrumentalist or positivist philosophy, focusing on what can be measured while remaining agnostic or dismissive about underlying reality. The Copenhagen approach's main advantage is pragmatic effectiveness. For nearly a century, physicists have successfully used Copenhagen-style reasoning to make predictions, design experiments, and develop technologies. The interpretation provides clear operational rules for connecting mathematical formalism to experimental outcomes. It doesn't require belief in parallel universes or hidden variables or modifications to quantum mechanics. For working physicists focused on solving specific problems rather than philosophical questions, Copenhagen remains perfectly adequate. Yet Copenhagen faces serious conceptual difficulties that have motivated the search for alternatives. The measurement problem remains unresolved. What constitutes a measurement? Where exactly does the quantum classical boundary lie? Why should measurement cause wave function collapse? Copenhagen provides no answers, treating these as primitive concepts or denying their meaningful questions. This vagueness becomes particularly problematic in quantum cosmology, where the entire universe is the quantum system and no external observers exist. De Broglie-Bohm theory, also called pilot wave theory or Bohmian mechanics, offers a radically different approach. Developed initially by Louis de Broglie in the 1920s and later elaborated by David Bohm in the 1950s, this interpretation posits that particles always have definite positions, even when unobserved. The wave function exists as a real physical field that guides particle motion through what's called the quantum potential. Particles follow deterministic trajectories, determined by the wave function and their initial positions, but we cannot know those initial positions precisely, leading to the apparent randomness of quantum measurements. Bohmian mechanics is explicitly non-local. The quantum potential depends instantaneously on the entire configuration of all particles in the universe, allowing for faster-than-light influences that don't violate relativity because they cannot transmit information. Despite this feature, which many physicists find uncomfortable, the theory makes identical predictions to standard quantum mechanics for all experimental outcomes. It's a genuinely empirically equivalent alternative, not just a reinterpretation, but a different underlying ontology that reproduces the same observable phenomena. The main appeal of Bohmian mechanics is that it restores a clear picture of reality. Particles have definite positions following definite trajectories. There's no measurement problem because measurements simply reveal pre-existing positions, rather than creating them through wave function collapse. The theory is completely deterministic once initial conditions are specified. Many physicists who feel uncomfortable with the vagueness and observer dependence of Copenhagen find Bohmian mechanics philosophically satisfying. However, Bohmian mechanics faces its own challenges. The theory's extension to relativistic quantum field theory, which describes particle creation and annihilation, remains controversial and technically complex. The non-locality, while not contradicting relativity's prohibition on faster-than-light signaling, strikes many physicists as an ugly feature that suggests the theory might not be fundamental. The particle trajectories, though definite, can never be directly observed, raising questions about whether they're truly explanatory or merely mathematical artifacts. And the theory requires both particles and wave function as fundamental ontology, which some view as ontologically extravagant compared to many worlds, which requires only the wave function. Objective collapse theories take a different approach, modifying quantum mechanics itself to incorporate spontaneous wave function, collapse as a physical process. The most developed version, the Ghirardi-Rimini-Weber theory and its descendants, adds random collapse events to the Schrödinger equation. For individual particles, these collapses occur extremely rarely, preserving quantum behavior in microscopic systems. But for macroscopic objects containing many particles, the collapse rate scales up, causing rapid localization and preventing superpositions from persisting in large systems. This approach elegantly solves the measurement problem by making collapse a genuine physical process that happens spontaneously rather than being triggered mysteriously by observation. The theory makes slightly different predictions from standard quantum mechanics, potentially allowing experimental tests. It maintains a single definite reality without requiring parallel worlds or hidden variables. And it extends naturally to all systems, including the universe itself, avoiding Copenhagen's measurement problem. The challenges for objective collapse theories include specifying exactly how the collapse mechanism works and why it has the particular mathematical form proposed. The theories introduce new fundamental constants that must be chosen to match experimental constraints while making collapse negligible at microscopic scales, but effective at macroscopic scales. They predict a tiny amount of energy non-conservation during collapse events, which could potentially be tested, but hasn't been observed. And extending the theories to relativistic quantum field theory while maintaining Lorentz invariance proves technically difficult. Quantum Bayesianism, or cubism, represents yet another interpretive direction. treating quantum states as expressions of subjective belief rather than objective physical properties. In this view, the wave function encodes an agent's degrees of belief about future measurement outcomes, similar to how probabilities in classical statistics represent subjective uncertainty rather than ontological randomness. Wave function collapse simply represents updating one's beliefs based on new information obtained through measurement. Cubism dissolves the measurement problem by denying that wave functions represent physical reality requiring explanation. There's no mystery about collapse because it's just belief revision, not a physical process. The interpretation embraces the subjective, agent-relative character of quantum mechanics rather than trying to eliminate it. Different observers can assign different wave functions to the same system based on their different information states, and this creates no contradiction because wave functions are personal rather than objective. Critics argue that cubism fails to explain why quantum mechanics works so well if wave functions are merely subjective beliefs. Why should personal degrees of belief evolve according to the Schrödinger equation? Why should different agents' beliefs, if they're truly subjective, lead to consistent predictions when they perform the same experiments? Cubism advocates respond that the theory does impose consistency constraints on rational beliefs, and that the success of quantum mechanics reflects the structure of rational inference rather than mirroring an underlying quantum reality. Relational quantum mechanics, developed primarily by Carlo Rovelli, occupies similar conceptual territory to cubism but with different philosophical commitments. This interpretation holds that quantum states are not absolute but relational, meaningful only with respect to other systems. When System A measures System B, the outcome is real for A, but not necessarily for a third System C that hasn't interacted with the A-B combination. Different observers can legitimately assign different states to the same system based on their different relational perspectives. The appeal of relational quantum mechanics is that it takes seriously the role of interaction in quantum mechanics while avoiding both collapse and parallel worlds. It maintains that quantum mechanics provides a complete description of nature, but denies that this description is observer-independent in the classical sense. The interpretation connects naturally to certain approaches to quantum gravity, where the relational structure of space-time might be more fundamental than absolute space and time. Challenges include making precise what counts as a reference system and how relational states compose to describe complex situations involving many interacting systems. The interpretation seems to imply a kind of perspectivalism where different observers have genuinely different but equally valid descriptions of reality, raising questions about whether there's any observer-independent truth about the universe. And like cubism, it must explain why relational states evolve according to the quantum mechanical equations rather than some other formalism. Quantum mechanics in the real world. Beyond the abstract philosophical debates about interpretation, quantum mechanics manifests in concrete phenomena throughout the natural world and modern technology. Understanding these real-world quantum effects provides grounding for the interpretive questions while demonstrating that quantum mechanics, however strange its implications, describes actual physical processes that shape our universe and enable contemporary civilization. Quantum tunneling represents one of the most dramatic departures from classical physics. In classical mechanics, a particle lacking sufficient energy to surmount a potential barrier simply cannot cross it, just as a ball rolled toward a hill will roll back if it doesn't have enough kinetic energy to reach the summit. In quantum mechanics, the wave function extends into classically forbidden regions, creating a non-zero probability that the particle appears on the far side of the barrier despite lacking the classical energy required to cross it. This tunneling phenomenon enables radioactive decay, where atomic nuclei spontaneously emit particles that quantum mechanically tunnel through the potential barrier holding the nucleus together. The decay rates calculated from quantum tunneling probabilities match experimental observations with extraordinary precision, providing powerful evidence for the reality of quantum effects. The age of rocks and the history of Earth are dated using radioactive decay, making our understanding of geological time and planetary evolution dependent on quantum mechanics. Tunneling also plays crucial roles in stellar fusion. The temperature at the core of the Sun provides particles with substantial kinetic energy, but not quite enough to overcome the electrical repulsion between positively charged nuclei through classical means alone. Quantum tunneling dramatically enhances the probability of nuclear fusion reactions, allowing them to occur at rates high enough to power stellar burning. Without quantum tunneling, the Sun would be unable to generate energy through fusion, and stars as we know them could not exist. Life itself depends on this quantum phenomenon. Modern electronics relies fundamentally on quantum tunneling. Flash memory, used in USB drives, solid-state hard drives, and smartphones, stores information by trapping electrons in insulating barriers through quantum effects. Writing data involves applying voltage to tunnel electrons through the barrier in one direction. Erasing data tunnels them back. The entire information technology revolution rests on engineered quantum tunneling in semiconductor devices. Scanning tunneling microscopes use quantum tunneling to image individual atoms, revolutionizing nanotechnology and materials science. Quantum entanglement, another phenomenon with no classical analog, has evolved from a philosophical puzzle to a practical resource. When quantum systems become entangled, measurements on one system instantaneously influence measurement results on the other, regardless of the spatial separation between them. Einstein famously derided this as spooky action at a distance, believing it revealed quantum mechanics to be incomplete. Yet decades of experiments, beginning with tests of Bell's inequalities in the 1970s and continuing through increasingly sophisticated demonstrations, have confirmed that entanglement is real. The resolution of the apparent paradox is subtle. Entanglement cannot transmit information faster than light, preserving relativity's prohibition on superluminal signaling. The correlations between measurement results are perfect, but each individual measurement appears random. Only when results are compared afterward does the correlation become apparent. Different interpretations explain this differently. Copenhagen treats it as an irreducible feature of quantum mechanics. Many worlds views it as correlation between branches. Bohmian mechanics attributes it to non-local influences through the quantum potential. Regardless of interpretation, entanglement has become technologically useful. Quantum cryptography uses entangled photons to enable provably secure communication. Any eavesdropper attempting to intercept the quantum signals necessarily disturbs them due to the measurement problem, revealing their presence. Quantum cryptographic networks are already deployed in several countries, protecting sensitive communications with security guaranteed by the laws of physics rather than computational complexity. Banks, governments, and military organizations increasingly adopt quantum cryptography for critical applications. Quantum teleportation, despite its science-fictional name, is a real phenomenon using entanglement to transfer quantum states between distant locations without physically moving the particles encoding those states. The process doesn't violate relativity because it requires classical communication of measurement results, limiting the transfer speed to the speed of light. Nevertheless, quantum teleportation has been demonstrated over distances exceeding hundreds of kilometers, both through optical fibers and free space, pointing toward future quantum communication networks. Quantum sensors exploit quantum properties to achieve measurement precision impossible with classical devices. Atomic clocks, which measure time using quantum transitions in atoms, have achieved precision better than 1 part in 10 to the 18th power, losing less than a second over the age of the universe. This extraordinary precision enables GPS navigation, which requires synchronizing satellite clocks to within nanoseconds. Gravitational wave detectors use quantum squeezing to reduce noise below classical limits, making possible the detection of space-time ripples from colliding black holes billions of light-years away. Quantum computing represents perhaps the most ambitious attempt to harness quantum phenomena for practical purposes. Current quantum computers remain small, noisy, and limited in their capabilities, but the field advances rapidly. Google's quantum computer achieved quantum supremacy in 2019, performing a specific calculation that would take classical supercomputers thousands of years. IBM, Intel, and numerous startups are racing to build larger and more capable quantum processors. Applications in cryptography, drug discovery, materials science, and optimization problems could transform entire industries. The chemical bond itself is a quantum phenomenon with no classical explanation. The forces holding atoms together in molecules arise from quantum mechanical sharing of electrons between nuclei. The shapes of molecules, their chemical reactivity, the colors of compounds, all emerge from quantum mechanics. Chemistry is fundamentally an applied form of quantum physics. The pharmaceutical industry's drug design, the materials industry's development of new substances, even the flavors of food and the scents of perfumes, all depend on quantum mechanical properties of electron orbitals and molecular bonding. Quantum effects appear throughout biology, though the extent of their importance remains debated. Photosynthesis achieves remarkable efficiency through quantum coherence effects that optimize energy transfer in light harvesting complexes. Birds navigate using quantum entanglement in proteins in their eyes that allow them to sense Earth's magnetic field. Enzymes catalyze reactions using quantum tunneling to transfer particles through energy barriers. DNA mutations occur partly through quantum tunneling of protons between base pairs. The role of quantum mechanics in consciousness remains speculative and controversial, but quantum effects in biological systems are established facts. Even cosmology encounters quantum mechanics. The early universe underwent a period of rapid expansion called inflation, driven by quantum fluctuations in hypothetical inflation fields. These quantum fluctuations, stretched to cosmic scales by inflation, created the tiny density variations that seeded galaxy formation. The cosmic microwave background radiation shows patterns predicted by quantum fluctuations during inflation, providing evidence that quantum processes shaped the large-scale structure of the universe. The entire cosmos emerged from quantum mechanical processes in the first moments after the Big Bang. The measurement problem in detail. At the heart of all interpretive debates lies the measurement problem, the most profound conceptual puzzle in quantum mechanics. Understanding this problem in detail reveals why physicists have developed such diverse and strange-sounding interpretations. The measurement problem arises from an apparent contradiction between two aspects of quantum mechanics that seem impossible to reconcile within a single coherent framework. On one hand, when quantum systems remain isolated from measurement apparatus and observers, they evolve according to the Schrödinger equation. This evolution is deterministic, reversible, and continuous. The wave function smoothly changes over time, maintaining superpositions of different states. An electron's wave function spreads out in space, encompassing multiple positions simultaneously. A photon passes through both slits in a double-slit experiment, interfering with itself to create the characteristic pattern of light and dark fringes. The quantum state evolves in a perfectly predictable way, governed by precise mathematical laws. On the other hand, when we perform a measurement to determine which state a quantum system occupies, we always observe definite outcomes. The electron is detected at a specific location, not simultaneously, at multiple locations. The photon arrives at one point on the detection screen, not everywhere at once. The measurement process seems to collapse the wave function from a superposition of many possibilities to a single actuality. This collapse is random, with probabilities given by the Born rule, and it appears irreversible and discontinuous, violating the Schrödinger equation. The measurement problem asks how these two types of evolution can both be true. If the Schrödinger equation governs all quantum systems, and if measurement apparatus and observers are themselves built from quantum particles, then measurements should follow quantum mechanical laws. There should be no special collapse process. The measuring device should become entangled with the measured system, entering a superposition of having measured different outcomes rather than producing a single definite result. To make this concrete, consider a quantum measurement in detail. An electron in superposition of two positions, left and right, interacts with a detector designed to register the electron's location. If the electron is on the left, the detector enters a state we'll call detector registered left. If the electron is on the right, the detector enters detector registered right. Initially, the electron is in superposition and the detector is in its ready state. What happens when they interact? According to the Schrödinger equation, which governs all quantum evolution, the combined system evolves into a superposition. One term in the wave function describes the electron on the left and the detector registering left. Another term describes the electron on the right and the detector registering right. The detector becomes entangled with the electron, entering a superposition of having measured different outcomes. There's no collapse, just the evolution of a larger quantum system encompassing both electron and detector. But we never observe detectors in superposition. When we look at the detector, we see either detector registered left or detector registered right, never a fuzzy quantum superposition of both. This suggests that something breaks the Schrödinger evolution, causing collapse from superposition to a definite outcome. Yet we've added nothing new to the system except observation. Are observers special? Does consciousness cause collapse? Where exactly in the chain from quantum system to microscopic detector to macroscopic instrument to observer's brain does collapse occur? The Copenhagen interpretation responds by positing a fundamental division between quantum and classical worlds. Small quantum systems obey Schrödinger's equation. Large classical systems have definite states. Measurement represents an irreducible process where quantum systems interact with classical apparatus, causing wave function collapse. This answer works operationally, but leaves deep questions unanswered. What determines which systems are classical? Where is the boundary? Why should size or complexity matter for fundamental physics? Many worlds resolves the problem by denying that collapse occurs. The detector does enter superposition, and when you observe the detector, you become entangled too. One branch of the universal wave function contains electron left, detector registered left, and observer saw left. Another branch contains electron right, detector registered right, and observer saw right. Both branches exist, but they can't interact after decoherence, so each version of you observes only one outcome and remains unaware of the other branch. Bohmian mechanics solves the problem differently. The electron always has a definite position, either actually on the left or actually on the right, guided by the wave function. The detector's pointer always points in a definite direction, determined by the electron's actual position through the quantum potential. We observe definite outcomes because definite outcomes actually occur, not because of collapse, but because particles have definite positions all along. The wave function never collapses. It continues to evolve according to the Schrödinger equation, guiding particle motion through the quantum potential. Objective collapse theories modify the Schrödinger equation to include spontaneous collapse. When the electron detector system reaches sufficient size or complexity, the modified equation causes rapid localization. The superposition spontaneously collapses to one term or the other through a physical process analogous to radioactive decay. This collapse is random, occurring at rates calculated from the theory's additional postulates, and it produces definite outcomes without requiring observers or classical apparatus. Each solution has costs and benefits. Copenhagen avoids ontological extravagance, but leaves the measurement problem unsolved, treating collapse as a primitive process. Many worlds accepts infinite branching universes, but preserves the unmodified Schrödinger equation. Bohmian mechanics restores definite reality, but requires non-local influences, and accepts unobservable particle trajectories. Objective collapse theories add new physics but introduce free parameters and energy non-conservation. No resolution is cost-free, which explains why the interpretive debate continues. Decoherence dynamics. Quantum decoherence, discovered and developed mainly in the final decades of the 20th century, transformed understanding of how quantum systems transition to classical behavior. While decoherence doesn't solve the measurement problem in the sense of forcing acceptance of a particular interpretation, it dramatically clarifies the mechanism by which superpositions become effectively classical. providing crucial insights that shape all modern interpretations. The key insight is that real quantum systems never exist in perfect isolation. Even in carefully controlled laboratory experiments, quantum systems interact constantly with their environments through photon exchanges, air molecule collisions, thermal vibrations, and countless other channels. These environmental interactions cause the quantum system to become entangled with environmental degrees of freedom, rapidly suppressing the interference between different terms in the superposition. Consider a molecule in superposition of two positions, separated by a small distance. In perfect isolation, these two position states would maintain quantum coherence indefinitely, able to interfere and produce quantum effects. But in reality, photons from ambient thermal radiation constantly scatter off the molecule. Each scattering event carries away information about the molecule's position, entangling the photon's state with the molecule's location. After multiple scatterings, the environment contains a detailed record of which position the molecule occupied. This environmental entanglement destroys the coherence between the two position states. The two terms in the superposition become correlated with orthogonal environmental states, meaning they can no longer interfere with each other. From the perspective of any observer who doesn't have access to the complete environmental state, the molecule appears to have a definite position. The observer cannot detect the interference terms that would reveal quantum superposition because those terms involve correlations with inaccessible environmental degrees of freedom. The timescale for decoherence depends dramatically on system size and environmental coupling. For a single photon in carefully isolated conditions, coherence can persist for seconds or even longer. For a microscopic dust grain at room temperature, decoherence occurs in less than a microsecond. For a macroscopic object like a cat, decoherence happens essentially instantaneously, in timescales far shorter than any measurement could detect. This explains why we never observe cats in quantum superposition. Decoherence makes macroscopic superpositions effectively impossible to maintain, regardless of whether collapse actually occurs. Decoherence also explains why certain observable quantities, particularly position, seem privileged in determining which states can be distinguished classically. The answer lies in the nature of environmental interactions. Most environments couple primarily to position. Photons scatter off objects based on where they are. Air molecules collide with objects based on their locations. Gravitational interactions depend on spatial distribution. Position eigenstates are robustly stable against environmental decoherence because interactions with the environment don't change an object's position state much, while they do distinguish between different positions. Other quantities, like momentum or energy eigenstates, are more fragile against decoherence in typical environments. A particle in a definite momentum state occupies a spread-out position distribution. Environmental interactions that couple to position rapidly destroy momentum coherence. This explains the preferred basis problem, why we observe definite positions rather than definite momenta or superpositions of energy states. The environment effectively selects the observables that remain coherent, and for most realistic environments, those observables are approximately position. The decoherence framework allows precise quantitative predictions about when quantum effects should appear and when classical behavior emerges. Experiments testing decoherence theory have confirmed its predictions across many scales. Researchers have demonstrated quantum interference in increasingly large molecules, from simple diatomic molecules up to complex organic molecules containing hundreds of atoms. The interference visibility decreases as molecular size increases and environmental coupling strengthens, exactly as decoherence theory predicts. Quantum computing faces decoherence as its primary practical challenge. Qubits must maintain coherence long enough to perform computations, but environmental interactions constantly threaten to destroy the quantum information. Enormous engineering efforts go into isolating qubits from their environment, cooling them to temperatures a fraction of a degree above absolute zero, shielding them from electromagnetic radiation, and minimizing thermal vibrations. Even with these precautions, current qubits maintain coherence only for microseconds to milliseconds before environmental decoherence destroys the quantum state. Error correction schemes attempt to combat decoherence by encoding quantum information redundantly and detecting errors before they accumulate. Quantum error correction requires substantial overhead, with many physical qubits needed to create each error-protected logical qubit. Achieving fault-tolerant quantum computation, where errors are corrected faster than they accumulate, remains a major goal of the field. Success would enable arbitrarily long quantum computations, limited only by hardware reliability, rather than fundamental decoherence. For interpretations of quantum mechanics, decoherence has different implications depending on the framework. In Copenhagen, decoherence explains when and why wave function collapse appears to occur, providing a mechanism for the quantum to classical transition without requiring mysterious instantaneous collapse. In many worlds, decoherence explains why branches separate and become unable to interfere, making the multiverse structure natural and predictable rather than arbitrary. In Bohmian mechanics, decoherence describes why certain trajectories become effectively classical while others remain quantum. All interpretations benefit from decoherence theory's precise account of the emergence of classicality. The philosophical significance of decoherence is profound. It demonstrates that the appearance of wave function collapse and the emergence of definite classical properties arise naturally from quantum mechanics applied to systems interacting with complex environments. There's no need to postulate collapse as a separate process, though whether that means collapse doesn't occur or simply appears to occur remains interpretively ambiguous. Decoherence shows that environmental entanglement, not conscious observation, drives the transition from quantum to classical, removing consciousness from any fundamental role in quantum mechanics.